This is Physics 2212, Lab 2, Charge Tape Revisited. Introduction. The purpose of this lab is to further illustrate the electric forces between two pieces of tape and computationally model their behaviors in a deeper and more complex way, using a distributed line charge model over a point charge model. Results. The electric and gravitational forces are equal with a 1.96 times 10 to the negative 3 Coulomb. Models. The fundamental principles we're going to use in this lab are Coulomb's law, which shows that the electric force is equal to Coulomb's constant times Q1 times charge 2 divided by R squared times R hat. We're also going to use distributed forces. Gravitational force, which is the force of gravity, is gravitational constant times mass 1, mass 2 divided by R squared times R hat, and Newton's second and third laws. We are also going to be doing our lab under the assumptions that air resistance is negligible, which is similar to Lab 1. Additionally, we're going to assume that each piece of tape has an equal charge and also that it is an evenly distributed charge across the tape. So this is a bit of the experience that we did in Lab 1, the experiment we did in Lab 1 with some data that we retrieved. So the mass of the tape is 0.0002 kilograms. The length of the tape is 0.2 meters, the width of the tape is 0.02 meters, and the distance between tape A and tape B that we calculated in Lab 1 is 0.012 meters. All of these we're going to use as our constant in our code later. The charge of one piece of tape is 2.26 times 10 to the negative 8 coulombs. Our system in this lab is tape B, which is also the same as Lab 1. The surroundings is everything around it, which also includes tape A. So here's our code. As you can see, at the beginning we have to lay out all of our constants, including the mass of our tape, which is what we found from Lab 1, the distance, and the length from Lab 1 as well. After that, we can begin to assemble our electric field. This we did in Lab 0. After that, we have to define our U-tape as a line of point charges. After that, we can create the tapes and create our model. After this, we find the net electric and gravitational force, and we're going to model them as arrows. After we do all of this code, it should run to look a little something like this. As you can see, the magnitude of the electric force and of the gravitational force are 1.96 times 10 to the negative 3 coulombs. And this is modeled by the fact that the arrows are pointing up and opposite from each other. They're equal and opposite. Some possible sources of error in this lab, are error in measuring distance when we measured the distance in Lab 1, and also assuming the charges on both tapes are the same, which is probably unlikely in our physical lab. Discussion. What if you had modeled each of your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you get with your line charge model. The estimated value of the charge would be that of Lab 1 if modeled as a point charge, which was 5.603 times 10 to the negative 9 Coulomb. However, if modeled as a line charge, it would be 2 times 10 to the negative 8 Coulomb, the charge we found in this lab, and also the probably more realistic charge. Why do these estimates differ? Which value is more likely to be closer to the real value, and why? That of a line charge would be closer because it is more realistic to the behavior of charges in real life. The difference arises because gravitational force must equal electric force, so that's why we have to adjust the charge. Conclusion. In this lab, we modeled the charges on two pieces of tape as a distributed line charge instead of as a single point charge. We found this method to be more accurate than with the point charge model of Lab 1. Thank you.